All right. Okay. So thank you for the organizers for the invitation. The time difference is a bit hard for us in the US, but it's a nice conference. And thank you also for the people watching the talk. So I'll talk about two different topics. One will be cost of precise biochemical oscillations, and the other will be about active heat engines, and this would be periodically driven heat engines. The first one, Udo talked about in his talk, maybe he had like one slide about it. I probably talk a little bit more about it. And the second one is a different one. All right, so again, that's the overview. First, I'll talk about the free energy cost of biochemical oscillations. Here we have found a bound on what's the minimal cost that coherent oscillations have when you have biochemical oscillations. And the second one will be a second law. So what's the appropriate statement of the second law for an active heat engine, okay? And by active heat engine, I mean periodically driven ones, not steady state ones, okay? Those are different systems. And we have worked with periodically driven heat engines. All right, so first part, free energy cost of biochemical oscillations. So, if you want to think about biochemical oscillations, maybe you want to think about circadian oscillations. That might be the standard example. And so you take a biochemical system that oscillates, you put in a dark room. So imagine you would pick up a person, you put this person in a dark room. At some point, your clock is going to dephase. Now you should imagine a stochastic person, okay, not something made of 10 to the power of 23 molecules, but something made of 100 molecules or 1,000 molecules. So, here you have an example of a simulation of a model. It's called the activator inhibitor model. If you do a simulation, there is some chemical species that oscillates. If you make an average with fixed initial conditions, that would be looking at the correlation function. There will be oscillations, but there is exponential decay of the amplitude of the oscillations in the correlation function. That's because of noise, right? I mean, and the number of coherent oscillations is just the decay time divided of the period, okay? So, if your number of coherent oscillations is 10, that means that, by oscillation 100, probably if you look at two different time series, they're going to be completely dephased, right? Where your clock would be counting day 100, the other clock of the other oscillation is counting day 150 or whatever, okay? So the number of coherent oscillations roughly give you for how long can you oscillate in a way that probably two different series would most likely be coherent, okay? So again, the idea is I take the biochemical oscillator, I put in a black room, and I want to know for how long can it still maintain precision or for how long can it still maintain coherence, okay? So, if you give me a model like the activator inhibitor model, that's one model for biochemical oscillations. That's just a bunch of chemical reactions, right? I can write down all those chemical reactions. I mean, this model, of course, is going to burn some free energy. If you have an equilibrium model, if you're not burning any energy, then you cannot have oscillations. I mean, your correlation function will not display an oscillation. That's something you can show. So, if you give me a biochemical system like this one, it's going to burn ATP. So in this case here, when I do this cycle in this enzyme M, I burn ATP, and P would be a phosphorylated form of the enzyme. So I'm burning ATP. And the question is, if I want to have, let's say, 10 coherent oscillations, how much free energy do I have to pay for that? Is there a minimal free energy I have to pay for that? Do I have to pay, I don't know, 20 kBT, 20,000 kBT, whatever I have to pay for that? What's the minimal price of having a certain number of coherent oscillations? Okay, that's the question. We have answered, or that's why I'm giving a talk about it. So we would like to answer here. So you don't have to really understand this equation, but the point I want to make is the following. If you give me a system of chemical reactions like this one, I can simply go ahead and write down a master equation. I assume Markovian dynamics is a good approximation for chemical reactions, which is a safe assumption at this point. And I mean, again, if you give me all these chemical reactions, I can just go ahead and write down a master equation. It might look big. It might be something that you cannot understand by simply look at this slide. But whatever chemical reactions you give me, I can just go ahead and write down a master equation. So now let's formulate the problem we are looking at mathematically. So what we do is we look at a master equation, right? dp dt is equal to LP. L would be your Markov generator, or if you are a very mathematical person, this is the adjoint of the Markov generator. And so if I look at L, it has eigenvalues. The zero eigenvalue is related to your stationary solution. Then the first excited eigenvalue, the one with the smallest modulus of the real part, has a real part, and it might have an imaginary part. And I mean, if I assume that my correlation function is dominated by this eigenvalue because the next modes are just lower modes, then the number of coherent oscillations is going to be the imaginary part of the eigenvalue divided by the real part of the eigenvalue. There is a 2 pi factor because the period would be 2 pi divided by xi, okay? And the decay time is just xr to the power of -1, okay? So xr gives me the inverse of the decay time, and xi gives me the inverse of the period up to a factor of 2 pi, okay? So again, the initial problem was a physical one of looking at the coherent oscillations. The way you transform this into math is the way I calculate the number of coherent oscillations is simply by looking at the ratio of the imaginary part and the real part of the first excited eigenvalue of the stochastic matrix, okay? That's the mathematical problem. All right, so this is one aspect of the problem, which is the number of coherent oscillations. The other one would be the entropy production. So we want to look at the entropy production rate, which is this formula that I guess everybody here should know. And I mean, again, the number of coherent oscillations is a dimensionless number. So we probably want to look at the dimensionless number for the entropy. So the entropy has dimension of 1 over time, of course, or the entropy production, I should say. So we look at the entropy production during a period. Okay, so delta S is going to be, if I multiply sigma by 2 pi lambda I to the power of -1, which is the period of oscillation. So delta S is how much energy or how much entropy is produced during one whole oscillation of the system, okay? Now, our conjecture is that delta S must be larger than 4 pi square n, okay? So, you know, if you want to have 10 coherent oscillations, then you cannot have 10 coherent oscillations if you're not willing to pay at least 4 pi square multiplied by 10, okay? That's what this inequality means. Now, if you want to compare with the thermodynamic oscillation, in a sense, or sorry, the thermodynamic oscillator relation, what this inequality achieves, it achieves for the number of coherent oscillations what the thermodynamic oscillator relation achieves for the uncertainty of a thermodynamic current, okay? Now, this inequality can be violated if the number of coherent oscillations is smaller than 2 pi to the power of -1, then, which again is a very, very low number of coherent oscillations. I mean, in practice, I mean, you can look at these things if you're looking at this ratio of eigenvalues, but you know, if you're looking at the correlation function, you would not see any oscillation there. If you were looking at a real system, this is a regime where, I mean, you wouldn't be able to distinguish oscillations and noise by just looking at with your eyes to a time series of the problem. Okay, so the inequality is not true for any value of n, only if it's above this regime. But of course, it can only be violated if the number of coherent oscillations is really, really low. And, you know, any real biochemical oscillation will not be in this regime. Okay, but mathematically, it's a relevant thing if you are thinking about proving the bound. So let's now explain. This is again a conjecture. I'll try to explain how did we obtain this conjecture. Okay. Well, I mean, it's, you know, it's a very well supported conjecture. Okay, so the first thing you do is start with like a unicyclic network. So, you know, that would be just I have omega states in a cycle, and I define my thermodynamic affinity, right, as the product of the rates in the forward direction divided by the product of the rates in the backward direction. And if I assume these rates are uniform, I can calculate everything exactly. I can calculate the delta S exactly. I can calculate the n exactly, and then I can find a functional form for a functional form between the entropy that I do in one oscillation and the number of coherent oscillations for the case of a unicyclic network with uniform rates. Okay, and for now I'm just finding this functional form, and I'm kind of guessing that maybe my bound might be there. Okay, so that's pretty much why the reason. I mean, it's pretty much the only place where you can do these calculations. Otherwise, even for any cyclic network, this calculation would be pretty hard analytically, at least. So, I mean, uniform rates, unicyclic, it's pretty much the only analytical thing you can do. And, you know, we just have to hope that maybe the bound's going to be there. It turns out it's going to be there. And so for now, I'm just doing these calculations, and I will compare whatever I get numerically with this thing to see whether the bound reaches this value. So next thing, we have to do the numerical problem. So how do we do this numerical problem? The numerical problem is I try to find the minimal delta S, but I have to fix n. Of course, fixing n means you are fixing the ratio of the imaginary part and the real part of the first excited eigenvalue. Okay, that's not something very easy to fix. Again, analytically, I have no idea how to do that. Although numerically you can do that, right? You can simply tell your computer, please fix lambda I over lambda R and search for the minimal delta S. Okay, And if you do that, so you can do that for omega equals to 4, 5, and 6 and 7, you see that, I mean, the dotted line is what you get from the uniform rates, okay? The red circles is what you get if you just do a unicyclic network with arbitrary rates, and the blue symbols or crosses or plus sign, I should say, is what you get if you do a fully connected network, okay? If you put all your rates there. Again, the unicyclic network is a particular case of a fully connected network, okay? Now, the first thing you identify in these figures is that, you know, if the number of quantity oscillations is large enough, things are going to the uniform rates. If it's small, there is a regime there where actually uniform rates do not minimize, but the minimum is below uniform rates. But the other very important thing you realize here is that the fully connected network never does better than unicyclic network. So, you know, you can do omega equals to 4, 5, 6, 7. You can also do 8 and 9. After that, it becomes kind of hard. But for all the system sizes, what you realize is that unicyclic network, I mean, the fully connected network, which includes all possible networks at that size, because, you know, I can always set some rates equal to 0 when I'm optimizing things, will never do better than the unicyclic one. Given that that's true, we can restrict our investigation to unicyclic networks, because the fully connected or any other networks that not a unicyclic one is not going to do better when we are thinking about this trade-off between delta S and N, okay? And I mean, this is not trivial, because of course you can say unicyclic network should be the best one if you're only thinking about precision, right? If I have more cycles that are not my best cycle where I do the oscillations, then they just will make me less precise in a sense. But this is not totally trivial, because if you think about entropy production, I mean, if I have extra cycles, I can make my entropy production smaller, okay? I mean, if you decompose entropy production into a cycle decomposition, there are cycles that can give you a negative contribution. If the affinity of the cycle goes against the current, then that will make the entropy production smaller, okay? So adding cycles probably make your precision worse, but it could also make your entropy production smaller. So, I mean, we have this numerical evidence that you can never do better than unicyclic networks, but if you're thinking about the trade-off between precision and dissipation, that's not an obvious thing, okay? But okay, given that we have this evidence, we now can restrict to this case of unicyclic networks. That's what. So if we restrict to the case of unicyclic networks, then you can do much bigger system sizes, and you can get the asymptotic curve for very large system sizes, and that's how we find our bound. And as you can see, if n is larger than 2 pi to the power of -1, then delta S must be larger than 4 pi n squared. If you are below that, then uniform rates do not saturate the bound. It's something else, which we don't know what it is. You can go below the bound, but again, we can get this result. And physically, it simply means if you have 10 coherent oscillations, then you have to dissipate at least 4 pi squared multiplied by 10, okay? You can also see these things the other way around. Suppose you do not know anything about your energy dissipation. You go ahead and you measure correlation function of a biochemical oscillator. So people do that. There are experiments that achieve that. And typically they indeed do not know anything about the energy dissipation. So if you measure N, then of course, you can find a lower bound on the amount of energy you dissipate, okay? So you can see these things both way around. You can see it as the minimal energy you have to dissipate to achieve some precision, but you can always see once I measure this thing, this N, I can go ahead and infer about how much is my interproduction by looking at a single quantity. Again, if you think about the uncertainty relation, we here pretty much achieve for the number of coherent oscillations a correlation function can do, more generally speaking. What the uncertainty relation achieves for the precision of a current, we have here achieved for the number of coherent oscillations, okay? So we are saying what's the minimal cost of precision as determined by the number of coherent oscillations. Now, we have done like this Chi-C model, so that's real. By real, I mean I think that's a little bit closer to what people do in experiments. So, you know, Chi-C is a molecule that is you can find in cyanobacteria, and people do experiments where you just put Chi-C with Chi-A and Chi-B, which are other molecules in ATP, and you look at the phosphorylation of the Chi-C molecules, and it does oscillations with a period of 24 hours. Now you can do a model for that. It's, you know, a little bit more complicated model than this activator inhibitor model I showed you. But, you know, if we take data from this model, we can see that, you know, everything we get is in agreement if the bound is above the bound. So it's just a confirmation that if you do a more realistic model, and, you know, if the system size, if the number omega is the number of chi-C molecules in the solution, so if the number of chi-C is smaller, we see it's closer to the bound. But I mean, it's just for this model. I don't know how general this is. So, you know, I have no idea how close to the bound real systems operate. I mean, this is a totally open question. And so, you know, there are three interesting perspectives. One is inferring dissipation by looking at n, and the other is, you know, how close to the bound real systems operate. Okay, so that was it for biochemical oscillations. Let me now start with active heat engines. So, you know, heat engines are, you know, that's kind of the reason thermodynamics started. And we in stochastic thermodynamics got interested in heat engines. And now, when I say heat engine here, I mean a cyclic thing, okay? I mean a periodically driven system. So I'm not talking about steady state heat engines in this talk. So if we think about periodically driven heat engine in stochastic thermodynamics, in 2008, Udo Seifert and Tim Schmidt and Udo Seifert, they proposed a model. And this model was then realized experimentally in this experiment by Valentin Blickle and Bechinger. And you know, the model, I guess most of you are familiar with it, would be like you have a colloidal particle in an harmonic trap. First, I make the stiffness of the potential. I mean, I make the K of the trap larger. Then I change the temperature from red to blue, and then I change the stiffness again, and then I change the temperature again. That's a cyclic process. It's something like a Stirling cycle, right? And you know, you can extract work, and you know, you have the Carnot bound. And if you do an engine like this, again, this is different from standard thermodynamics, right? There are fluctuations, it's finite time, so it's different. We don't have these restrictions that we have to operate a very, very large system. Also, quantitatively, we can look at models at finite time in stochastic thermodynamics. So they are different from standard thermodynamics here. Again, I think most of you are totally aware of that. Now, this was, you know, this experiment was 2012. If I'm not wrong, the paper by Tim Schmidt and Udo Seifert was 2008. And but then in 2016, there was a very interesting experiment. I mean, I think for theorists, this poses a very interesting question. So you can do the same experiment, right? You put the colloidal particle, but now you put a bunch of bacteria in your bath, and then you can call this an active bath. And what they see, observations that you can see in the experiments is that you can extract more work if you compare the active heat engine with a passive counterpart, which would be you do again the same heat engine without the bacteria there. Another interesting observation is that your efficiency, which I would call the pseudo efficiency, which is the work divided by the heat. And again, this heat here does not take into account the energy dissipation of the bacteria, of course. That can go, you know, this efficiency, the pseudo efficiency can go above the Carnot efficiency. Those are probably the main observations done in this paper. And now the question that then we should ask probably is, what is the appropriate statement of the second law for this system, right? And I mean, a theorist, probably the first thinking of the theorist is say, of course, if I include all the energy that the bacteria dissipate, then I recover the second law. Then, you know, all this, of course, the efficiency can go above the Carnot efficiency because I don't take all the energy the bacteria dissipate into account. But that's not a very good answer because, I mean, the amount of energy the bacteria dissipate is probably way, way larger than whatever the engine is doing, the work extracted, or I mean, it probably way, way more. So if you were to look at the second law that also includes the energy dissipated by the bacteria, the second law would only tell you that the energy dissipated by the bacteria is positive. Okay, that's all it would tell you, because this thing would be so much larger than whatever else is happening, the work done by this engine. And when I say the work related to whatever you could extract from the colloidal particle. Okay, so you know, that's not a very satisfactory answer. So I mean, if you think about second law of thermodynamics, it tells us the kind of things you can do from what you cannot do, right? You cannot, for example, burn calories by taking the elevator, right? I mean, if you know, you could convert gravitational energy into burning calories, you know, with efficiency 1, that's in total agreement with the first law of thermodynamics. That would be great if it was true, but the second law of thermodynamics will tell you that you cannot do that. So the second law of thermodynamics tells us the kind of things we cannot do. And so, you know, if you want to find the appropriate statement of the second law for such system, you want a statement of the second law that you can tell you what kinds of things this engine can do and cannot do. And this should be measure. I mean, one thing this thing should fulfill is that it should not really have all the energy dissipated by the bacteria. and it should be only in terms of quantity you can measure. And in this case, for example, it's just the position of the particle, okay? So the second law should only contain things that I can calculate by simply looking at the position of the colloidal particle and knowing nothing about whatever the bacteria are doing, okay? And that's what we did. Okay, so in order to do that, I will start with a very simple model for an active heat engine. Again, active is kind of a dangerous word. I mean, you know, it's sometimes a borderline synonym to non-equilibrium. At least in this context, I think I can define it with a mathematical equation. In general, it might be hard. But let's think about this two-state model. So I have a two-state system. Blue means cold temperature, red means hot temperature. And so, you know, at first I increase the energy of the upper level, then I decrease the energy, then I change the temperature, then I decrease the energy, and then I change the temperature back again. Now that would be a standard heat engine. This kind of thing has been done in the literature. This two-state heat engine, you can solve everything exactly. But now if I want to make it active, I put like a delta mu between the two states, which would mean like you could imagine these two states are two states of a molecule. There's a conformational change when I go from one state to another, and the delta mu I would be burning like ATP between these two states. Okay. Now I should say that this model is very different from the previous model in the sense that there is no coarse graining here. Now, in the previous model, if I look at X, I mean, I can only see X, I cannot see the position of the bacteria. Here I can see everything because there are only three states, okay? I will talk about the issue of coarse graining after, which is very important here. But I mean, all I want to point out here is that that's a very simple model. You can solve it analytically, even if you put the delta mu there. And it's the first model I would like to talk about for an active heat engine. And again, if delta mu is equal to 0, my heat engine is passive. Okay, a passive heat engine does not mean you are in equilibrium. It just means that you have a heat engine that, you know, the efficiency is going to be bound by the Carnot efficiency and everything else. But if I turn on the delta mu, the heat engine is active. And if I turn off the delta mu, the heat engine is passive. Now, mathematically, what it means is if I was to freeze my heat engine, if I was to stop the protocol, and I would wait for a steady state, if my steady state is an equilibrium one, I call this heat engine a passive one. If my steady state would be a non-equilibrium one, I call this heat engine an active one, okay? Andre, all right, so, yes, sorry.
Andre, can you just once again explain what this delta mu is?
Delta mu would be the free energy hydrolysis of one ATP. So, I mean, I would have like two possible chemical reactions going up and down. One would be the phosphorylation reaction, and the other would be the dephosphorylation. So this looks like a three-state model, but with two links. That's why I can burn ATP between these two states.
Okay.
So, you know, if you are in physiological conditions, delta mu would be 20 kBT. So it's the free energy of one ATP hydrolysis. All right. Okay. So, you know, that would be an active heat engine. And now, you know, if I go ahead and calculate everything from this active heat engine, again, it's an easy problem to solve. You can do everything analytically. I can get all the observations from the experiment. I can get that the extracted work of an active heat engine can be better or can be larger than its passive counterpart, which corresponds to delta mu equals to 0. And I can get a region, which is the blue region here, where the pseudo efficiency, which is the work divided by the heat, is larger than the Carnot efficiency. Okay, and I should point out again, when I'm talking about the heat, I'm only talking about the heat that comes from jumping between 0 and the up state. Okay, I'm not talking about the heat that is consumed the free energy hydrolysis of the ATP. This is I'm not taking into account. Okay, so I mean, if I look at this model, I can calculate everything. Okay, I can look at the standard second law for this model, and of course, if I look at the standard second law of this model, I recover the standard thermodynamics. And so QH again is the hot heat that comes from jumping between up and down. W would be the extracted work, and delta S active would be the active contribution. Okay, delta S active is just how much ATP I burn multiplied by delta mu. That's delta S active. Okay, so it's the free energy of one ATP hydrolysis multiplied by the rate at which I burn ATP. And again, all these quantities are over a period, okay? So they are how much entropy I produce in one period. Now, what you can see here is that the scaling of these quantities is different. The scaling with the period tau. So the problem I told you about in the experiment that, you know, the energy displayed by the bacteria is way more. Mathematically, you can put this problem even in a more serious case. I mean, the problem with this is that if I look at work and heat, okay, or I should call this passive heat again. It's just the heat that comes from the jumps. these things, they scale with tau in a way that, you know, if I make my tau very, very large, they saturate, they go to a finite value. But if I look at delta S active, which is, you know, how many times I do cycles, this thing never stops. Like if I make my tau larger and larger, these things increase linearly with tau. Okay, so the scaling of these terms in the introduction is different. So, which is again restate the fact that this second law is not a very good one. I mean, in the limit of large enough tau, it will only tell me that delta S active is positive. Okay, if I have a second law that tells me that delta S active is positive, it doesn't tell me anything about how much work I can extract, for example. Now, the good second law, the appropriate second law for this active heat engine is the second one. It comes from what's called the excess entropy. And if you do the excess entropy, you still get the heat, you still get the W, but you get this I term, which I'm going to talk about later. It's an information theoretic term. And this I term is in blue here. Now the I term has the right scaling, so it doesn't grow linearly with the time tau. And pretty much that's our result. The only thing I still have to talk about is coarse graining also. But what I should say about excess entropy, okay, that's a very well-known quantity in stochastic thermodynamics. So this comes from Hattan and Saha fluctuation theorem. So this thing has more than 10 years. Now, the excess entropy in a steady state is 0. So that's probably a main reason people have been interested in the excess entropy, but not that much. I would say the main interest on it was that, you know, it alone fulfills the fluctuation theorem. So there is the excess entropy, the housekeeping entropy, and the total entropy. And each one of them fulfill the fluctuation theorem. So I think that was a main reason of interest. Again, excess entropy in a steady state is 0. For a periodically driven system, not 0. It's this thing here. And it turns out that the excess entropy, or I mean, some people may call this non-adiabatic entropy. Okay, that was the work of Massimiliano Esposito and Van den Broek. They called it non-adiabatic entropy. I mean, there is a difference on boundary terms, but for a periodically driven system like this, both of them would be the same. The first point I'd like to make here is that the appropriate statement of the second law for active heat engines that are cyclic, that are periodically driven, comes from the excess entropy, okay? And that's pretty much the second law we get. Now I'm going to do two things. I'm going to try to explain what this term I here is, try to explain how these things look in general. And I also would like to talk about coarse graining, because I didn't talk about coarse graining. Coarse graining is also a very important point here. Again, a major point here is that this second law does not have the problem of scaling, okay? So this problem of scaling shouldn't be hard to understand. I mean, if I look at the delta S active part, that's something, you know, if you think about the bacteria in the experiment, I mean, of course, if I make my tau larger and larger and larger and larger, while my work saturates in the experiment, my work per period saturates, the amount of energy the bacteria dissipate is just growing linearly with time, right? I mean, in a steady state, you just burn energy linearly with time. So, you know, again, this second law, which is the standard second law in stochastic thermodynamics, is not a very good second law for this case. Okay, so let's just see how these things would look like in general. So, you know, the way to do that is you look at a master equation like this one. And, you know, since it's a periodically driven system, your transition rates are going to be time dependent, and they will be periodic in time with a period tau. Tau would be the period of the engine, right? If your temperature and energy depends periodically on time, then that's how your transition rates should depend. Now, if I look at a master equation like this, there's like a long time limit solution. And this long time limit solution also is going to be periodic in time, right? I could call this periodic steady state. Some people call it this name, but, you know, P of t here denotes the solution, the long time solution of this equation, which will also be periodic in time with a period tau, okay? But now there is a different kind of probability, which is the stationary solution I would reach if I were to freeze the protocol. So if I would stop changing my temperature and my energy and just, you know, look at what's going to be my stationary solution, then that's what's called accompanying density sometimes, or accompanying probability distribution. That is what I'm calling PS, okay, which would be just the solution of this equation, right? The stationary master equation for that particular time t, okay? Of course, both P of t, the solution of the master equation long time limit, and PS of t are both time dependent, and they are both periodic in time with period tau, okay? Now, here again, I can give a mathematical definition to what is active heat engine, what is a passive one. The active heat engine would correspond to the case where this PS would go to the equilibrium distribution. This would be the passive one. And the active one is during part of your time interval, the PS is not the equilibrium distribution, then that would be an active heat engine. Okay, that's again mathematical definition. In this context, at least you can give a mathematical definition to the word active, which I think sometimes I find it a bit confusing. I mean, it can almost be a borderline synonym to non-equilibrium active. But here, again, passive means PS will be P equilibrium, and active means PS is not P equilibrium, at least during part of your priming interval. Okay, so there are, again, it's very important to realize here there are two distributions. One is the distribution of one is the solution, the long-time solution of the master equation, which is the real distribution of the system, and the other is the distribution of the system would have if I was to stop my protocol and wait to go to a stationary state. Okay. All right. So if we go ahead now, so what you do is you write your transition rates with the generalized state balance condition. Now, generalized state balance is not really a condition; it's a physical interpretation of transition rates. I mean, we should really rethink this name. Generalized state balance is fine, but condition is not really best choice of words. So, that's a physical interpretation for transition rates. That's how you relate your transition rates to physical parameters. Now, beta is temperature, delta E would be your free energy difference between J and I, state J and I and J are states. So, if I'm thinking about the experiment, this could be the position of the colloidal particle, or if I'm thinking about that model, it would be either M state up and down. Okay. And beta C minus 1 is just your temperature. A alpha would be the external affinity. So, if I'm thinking about ATP, burning ATP, the A alpha would be the free energy of 1 ATP hydrolysis, and Dij are the distance. So if, for example, going from I to J, I burn 1 ATP, then Dij would be 1. If I go from J to I, Dij would be minus 1. And if I don't do anything, it would be 0. Okay, that would be by Dij. So again, that's just a physical way of writing your transition rates. If you take this thing and you're using the expression for the entropy production, you can easily derive the expression for the entropy production. I mean, so you can easily show that your entropy production is going to be one distribution, which is just the sum of all affinities, alpha, A alpha, J alpha. Then you have the generalized heat current. Again, if you just have a case where you have a hot reservoir and a cold one, that's just going to be your hot heat. And then I have the work. Okay. Now, if you do the same thing for the excess entropy, that took some work to realize this kind of thing. It was not that easy, but I mean, that's the definition of the excess entropy. Okay, that's well known. Now, I mean, the first thing we realized about the excess entropy was that it didn't have the problem of scaling with tau. Okay, but then I mean, we realized that the excess entropy had this nice decomposition. So there's this I term, it will have the hot heat term, and it will have eta C. Here is the Carnot efficiency. Okay, in case I didn't tell you, and W is the work. Okay, so that's what you get if you do the excess entropy. Okay, that's pretty general. I mean, this works for pretty much everything. The only underlying assumption is that Ij here is Markovian dynamics. Okay, now if you think about the experiment, when I say state I here, state I would be the position of the particle plus the position and whatever other variables I need to determine the state of the bacteria. Okay, so I here is really the state of the whole thing. Okay, that's the idea, and I'm going to talk about coarse graining in a couple of slides. Okay, so again, I mean, the only assumption I'm making here is that at some level of description, so if you think about the experiment, if I take the colloidal particle together with all the bacteria, there should be some Markovian dynamics at some level of description, okay, which is a mild assumption. Okay, so that's, if I look at this equation, I can just tell you what I would be, and I will be something like that. Okay. Now, the first thing you realize here is that if I have a passive heat engine, which would mean that PS would be P equilibrium, then the I term is going to be 0. Okay. So if I have a passive heat engine, this I term is 0. And this I term is an information theoretic term that quantifies the difference between PS and P equilibrium. Okay. It's not really about the probability distribution you have. It's more about the probability distribution you would have if you were to reach a stationary state. Okay. So let me give you a clear information theoretic expression to I. So the
Andre,
way you do that
just to interrupt briefly, you have 2 minutes plus 5 for questions.
Yes, that's fine. That's perfect.
Fine.
if you were to look at this quantity ln of PS or P equilibrium average, you can write it like this. That's actually the Kullback-Leibler divergence of P and P equilibrium minus the Kullback-Leibler divergence of P and PS. Now, if I take the time derivative of this quantity, I will obtain these two things. If I integrate over time, of course, the left-hand side of this equation, this equation here has to be 0 because ln of PS over P equilibrium, the average of this is periodic in time. So if I integrate from 0 to tau, the derivative of something periodic in time, I'm going to get 0. And so, you know, you can either take I to be this term here, which is what I took there, or you can take I to be this term here, okay? So one of any of the two. So I is part of the time derivative of this Kullback-Leibler divergence difference here, okay? That's the information theoretic interpretation of I. So it pretty much is an information theoretic term that measures how different is the stationary equilibrium would have if you were to relax to a stationary state in comparison to the equilibrium distribution, okay? Okay, so I don't have to talk much about coarse graining. So again, if you think about the experiment, I would be the total state, X would be the position of the particle, and A would is what determines the position, the state of the bacteria, okay? And, you know, of course, if I write down the master equation for the X variable, I'm going to have these K rates here, which are not really rates. So this is not really Markovian dynamics anymore for the X, okay? And the nice thing about coarse graining, I don't have to comment too much about that. I mean, of course, technically it was not so easy to find it out, but when you do the coarse graining, I mean, what you find out is that the second law retains the exact same structure, okay? You have some coarse grained dye, which has the exact same form, and you have the coarse grained heat, which has the exact same form, and the work has the exact same form. So, I mean, if you do the coarse graining, everything remains the same. Again, Esposito has a paper from 2012 about the standard end production in stochastic thermodynamics. That's the same property. You do coarse graining, and the end of production retains the same structure, okay? Now we can go ahead and do a more complicated model that's more like the experiment. So this would be like, you know, you do a passive particle interacting with a bunch of active particles. You can only see the passive particle, and you can look, for example, the pseudo efficiency, which would be I divided by QH, and I can define like a correct efficiency, which accounts for the QH and the I, and I can see that, you know, the correct efficiency is always below the Carnot efficiency, but the pseudo efficiency can go above. Again, this is a way more complicated model than the first one I showed. That's more like the experiment. Okay, it's a 2D model with a passive particle and the active ones. But the point here is that, you know, if you do coarse graining, it doesn't really matter in the sense that everything remains the same. And I mean, the physical interpretation here is when you have an active heat engine, it's not really about how much energy is dissipated. It's more about how you shift your distribution, how you shift your stationary distribution from the equilibrium one, or the stationary distribution you would have from the equilibrium one to a new stationary one as quantified by this term I, okay? And with that, I conclude. So I told you two different things. One was about the minimal free energy cost of coherent biochemical oscillations. That was work with Lucas Oberreiter and Udo Seifert. And I talked about the second law for active heat engines. That was work with my PhD student, Arya Data, Patrick Pietzonka, and both of them are archived. Thank you for your time.
Thank you very much, Andre. Any questions?
Hello, Andre.
Yeah, please.
Andre, you were saying that when you are defining your efficiency, this information term is acting like a fuel. So it should be added to the absorbed heat.
I would say that, you know, when you have an active heat engine, the only risk, I mean, you can use two results to do work. One is the heat you take from the hot reservoir, more or less. I mean, it's a bit of a dangerous statement. Of course, in the first law, you only get the hot heat, but in the second law, there is also the I term. And I mean, for example, even if I do beta C equals to beta H, okay, even both temperatures are the same, and I have no QH, I can still do work in an active heat engine. Okay, so I mean, and I mean, the main point here is that, you know, the amount of energy the bacteria is dissipated is not really important. The important thing is the information theoretic term. It's how these distributions are shifted as quantified by this information theoretic term. If that answers your question, I'm not sure.
And one more question: can this Carnot efficiency be cast using effective temperatures so that it stays below the Carnot efficiency, the efficiency?
I mean, I'm not a great fan of effective temperatures, but I mean, the whole point of doing that was to avoid effective temperatures. So, you know, here I work with bona fide temperatures. They are real temperatures, and I don't have to talk. Now, you can, I mean, you can define effective temperatures. There are different ways. You can do it by, for example, assuming it's a Boltzmann distribution, or by looking at the sort of fluctuation dissipation theorem kind of thing. And for certain models it will work, and for other models not going to work. But which is not the case of our second law. It works for our models. That's the comment I would make about effective temperatures. So if you do effective temperatures, you can look at a certain model. It's probably going to work. It's going to be a good description there, and then you can define some kind of efficiency, and everything is going to work. But in general, I think it's not going to work for sure. If you do a simple analytical model, you can see that pretty easily.
I see.
Question from Saha. You need to unmute.
Yeah, thank you. I was just wondering, how general do you expect this result to hold? So I think you have shown this now for 1 or 2 models, but it looks quite general. What do you think about that?
Yeah, it holds for everything. So I mean, as long as at some level of description your dynamics is Markovian, it holds. So if you think about the experiment, you have a passive particle, right? If you only look at the passive particle, then the dynamics is not Markovian. But if you include also the bacteria in the description, there should be some level of description where things become Markovian. And I mean, if you think about like biophysics, that's true for everything. Again, if you do something quantum stuff that is, an open quantum system that is truly no Markovian, then maybe your life is going to be hard. But I mean, if you're thinking about stuff in biophysics, for pretty much, so I mean, I would say if you have a periodically driven system in active matter, the second law is the right second law.
So from that, we can conclude that the only way of boosting the efficiency is to have a state where this steady state probability is different from an equilibrium one. And if you happen to have an active matter system that has the same PDF but different dynamics, that would not help to boost the efficiency, right?
Yeah, I mean, the active system never really have the same PDF. I mean, you could have a Boltzmann-like distribution, but then it's going to have an effective temperature. It's going to be a different distribution. But yeah, I mean, I would even say that the thing that really tells you how better you can do, or how much better you can do, is quantified by this I term. That's what quantifies. I mean, it's not really about how much energy you're dissipating. If you dissipate energy, it can be totally useless, but it's really about how you shift the distribution.
Yeah, thank you.
So we have time for one last question, which is from Edgar.
Yes, so I was wondering, okay, first, I don't know if this is true, but this second law is also true for things that are not active matter. It could be something that the accompanying density is not equilibrium, it could be whatever. So if there is a non-conservative force, this could be also the case, no? So you don't need activity, biological activity. It could be right?
Yeah, I mean, yes, it's true. It's true for everything. I would say, as long as dynamics Markov is true. Now, the word active again is a very dangerous word. I would say, I mean, again, it's what I'm calling active here by definition is if my steady state would be a non-equilibrium one, then I call it active. And I mean, probably people would call active matter, of course, right? Matter when there are dissipative degrees of freedom I cannot see, and so that would be more a matter of coarse graining, I guess. But the point is that when you do coarse graining, the structure of the second law remains the same. Doesn't really matter. I mean, it's something that you have to work out, but the structure of the second law is the same whether you do coarse graining or not, and everything can be measured only in terms of the coarse grain variable. So whether you want to call it is inactive matter or not, everything should work the same.
And if you do this with the housekeeping heat instead of the excess heat.
So what the housekeeping, I didn't tell you what the housekeeping heat will tell you. It will tell you that this delta S active term is larger than the I. So even for a small tau, it doesn't matter the size of the tau, the delta active term is always larger than the I. So the delta S active is like how much you are paying for this information term, if you want to think like Maxwell demon kind of thing. So that's what the housekeeping heat will tell you.
Okay, so I know that Victor Hollyberg wants to ask a question, but I think we do need to draw this session to a close now. So thank you again to all of the speakers in this afternoon session.